Welcome back to the bench. This is a Fluke 343A DC voltage calibrator. Hoping I can get this into my calibration rack once we get it cleaned up, tested, and calibrated. This was one of the reasons for the new 7510 meter, so I can calibrate this, so I can use this to calibrate my other meters. This one's got some damage to it. It's not sitting flat, it's missing a foot. Big divot in the back of the power supply. You guys, or in the back of the board, you guys can see that where the case is bulged up back here. It took a big hit right here, and so it's kind of damaged, but not terrible. I got it hooked up to the current limited variac supply, so let's set that there. We'll go ahead and give it some power. I wanted to bring you guys along for the initial smoke test, so we will turn it on and see what happens. And we're drawing about 14 watts, 13 watts. I heard something click. See if that's normal. Must be, it sounds like it's shorting some stuff out. When I turn it on, there's a contactor that goes. But 2 volts in the meter. We're only running about 18 watts. Let me kick this over into my unisolated supply so I can use one of my bench meters for it. The isolated ground will cause it to float relative to the meter, and on the EDC I was actually getting overloads because the EDC floated up about 500 volts above ground. So move this over here real quick. We're not 13 watts is fine. We're in the 110. We're on the unisolated supply, so not going through the isolation transformer at the moment. Still 13 watts. Let's put this... All right, well, let's see what kind of accuracy we can get out of this thing. There's a thump. Let me move you guys over to the meter. Take note of the display reading. We are on the 10 volt scale, and we are at 10.000000 volts. Well, I think that'll do. So, looks like this thing may need some TLC. We'll go through some ranges, put it through its tests, make sure it's good for the lab, and then see how it goes. But I'm happy with that. Here's our first look with the cover off. This thing got hit so hard. I got a bunch of dents I'm going to have to take care of in the panel. You guys can't even see that. There we go. One of the screws fell out. So I got a bunch of dents I got to take care of in the panel. This is really abused. This thing got whacked so hard, this under panel has 2 dents in it, and this thing got shifted backwards in the unit. So I don't know what this thing got hit by, but it got hit by something big and heavy. So it's a miracle the boards didn't crack or anything like that, or stuff's not rolling around inside this case. Big power transformer in the back, power supply section. This is the analog reference section. You don't want to touch anything on this board with your bare hands. The leakage currents need to be so low on this board to get the accuracy up that if you touch anything with your hands, you have to clean it afterwards because your oils will cause leakage even through the circuit board. So I will get this straightened up, work on hammering these dents out, see what I can do about making a foot for this, because the foot that's actually busted is the one back here in the back. That's why it's like that. But if I hold it up like there'd be a foot back there, everything actually goes back to square pretty good. So need to get that addressed, get a foot for back there. But all in all, I am not unhappy with that. Needs a little bit of TLC, but we'll see what we can do. What a difference a bath makes. So I've got all the knobs off the front of the unit. These are unobtainium, so I can't buy any new ones at the moment, which is kind of unfortunate because one was cracked when I got it. So I noticed the crack as I was taking the knob off. So we'll have to go ahead and fix that real quick. Probably have to do a little bit of polishing on it after I glue that back together, because the super glue will probably discolor some of this plastic, but that'll just polish right off again. So I will work on getting that fixed, and I will be back. So I hammered out all the huge dents on the top of the case. Don't have any paint that's this color, so I don't want to strip it down completely and take it to bare metal and repaint it, but it's good enough for now. I checked its accuracy, and I even checked its accuracy on my 6.5 digit multimeter and my 7.5 digit multimeter, and it can lock both of them. The 7.5 bounced around a little bit. I'll cut in some long-term measurements with this once I get everything put back together and all set. I can verify that my 6.5 digit multimeter is in spec with this thing. It'll lock the full 6.5 digit. It's just, there's no movement whatsoever. So very nice unit, regulating very well. Everything's working. So I will continue with the cleaning, and then we will see where it goes. And here the unit is after a bath. So we got the unit all cleaned up. Everything looks good. Knobs put back together. I'm on the lookout for another knob. This is the one with the crack in it. You can barely even see it. But at the moment, they seem to be unobtainium. So can't grab those. So since there's nothing to fix, I figured what I would do. I've already tested this, kind of let it sit there and run, and it didn't even hiccup. Everything was good. It just burned overnight. Or not overnight, but all day yesterday, and it'll put out 10 volts all day long, and it's nice and stable, so no problems there whatsoever. So what I'm going to do is I'm going to let it progress, or I'm going to fire it up, let it run all night tonight. I'm going to record some data. I'm going to use the 2 meters that I've got, and I'm going to start it up from cold, and I will go into why units need warm-up time, but then I will also go into, we'll talk about some accuracy after everything's all warmed up, and how I was able to determine it was in spec. So, because that gets pretty muddy. So what I'm going to do now is to start collecting the data. I'm going to fire up the meter in the unit, and I'm going to get the meter hooked up. Now I'm going to use the 7510 for this, so we'll set it to 10 volt range, 10 volts even. Yep, all that's right. So as soon as the meter boots up, I'll set up the parameters of the meter, which will be 15 power line cycles with filtering, so as accurate as the meter can get. It'll take the slowest amount of measurements. And then I'll hook this up and I'll turn this on as soon as possible. Now, the spec sheet calls for a 1 hour warm-up time on this and an hour and a half warm-up time on the 7510. Now, the warm-up time on the 7510 is so important that it actually logs in the meter when the warm-up time is complete. Doesn't do that on the 6500, but it's less of an issue. The LTZ 1000 has to get up to temperature in the 7510. So I will get that all set up. We'll collect the data, and then we'll go through some data. Okay, and now we can see the effects of the warm-up time. So it is 2 hours and 30 minutes, 23 minutes later, 30 minutes later. Beginning 10 minutes, 43 minutes, hour 17, hour 50. Right about here is when the meter hit its warm-up spec, but it's still trended down. The warm-up spec on here is, or on the Fluke, is an hour as well. But if that's kind of useless data. So we can see the trend drift down. It stayed around 10 volts, but we had a maximum reading of 10.00015, and we had a minimum reading of 10.000002, and we have a current reading of 18. So as the meters warmed up and stabilized, this voltage trended down, and now we can trust the measurement. We can, because the warm-up time has concluded, we can take accurate measurements. Now, this is not a low thermal EMF cable, so this is good test lead, but not the best test lead. This stuff is good test lead, but not the best, so I could do this setup with a little bit better cable, but the accuracy's here. I'm going to move down to some graph paper, and I'm going to run through as little math as I possibly can just to kind of prove out the spec and how it kind of works, and we'll go from there. Okay, here's some of the data sheets for both the 7510 and the calibration generator, or the DC calibrator. The 341A is the lesser unit, not lesser unit, but less precise unit. We're working on the 343, so we're on the 10 volt range. So our accuracy, whichever is greater, is 0.003% of setting or 0.00003% of range. We're at the top end of the range, so it's going to be this 0.003% of setting. We are dealing with percentages here. So this is 0.003%, not times 0.003. So when I do the math, I actually have to add 2 zeros to the front of this because it's a percentage. So when I'm actually doing the math, it's plus minus 0.00003. That's when we actually calculate out the uncertainty of the Fluke. So when I do that, we're on the 10 volt range. Okay, I'm going to use the higher accuracy spec because I misread that in the beginning. So we have a set point of 10 volts. Our greater accuracy is the range setting. So 0.00003%. So you add 2 zeros in the beginning because it's a percentage when you do the multiplication out. So it's 10 times 00 for the percentage, 0003, which gives you a 30 microvolts plus minus on the tolerance. So it can be high or low 30 microvolts. As I'm recording this, it's still trending down a little bit. So given a 30 microvolt tolerance on the 10 volt setting, we have a high being 10 plus 30 microvolts. We have a low being 10 minus 30 microvolts. We have an actual reading of 10.000013, 13 microvolts. So we're 13 microvolts high on 10 volts, but we are smack dab in the middle. Not right in the middle of the tolerance. We're a touch high, but it's still even trending down. If I look at the graph The graph is still trending down. That's why when you go to a cal lab, this gear runs 24/7. It's just plugged in and on and warmed up, and it's all for stability. So the DC references, the AC references, all that stuff runs 24/7. They just burn the power. The meters probably even stay on. Some of the key meters in a cal lab probably stay on. Also, the rooms are humidity controlled, temperature controlled. It's one of the reasons why I was monitoring the temperature, because I would have to take into account the temperature coefficient of both pieces of equipment if I was outside the temperature range. I'm not. We're right at about 20 degrees C in my lab. Let's see. .25 degrees C. So the cal spec on these is 23 degrees C plus minus 5 degrees. So we're within specs. Everything's good there. So one other good metric to look at, which is how stable the supply is this standard deviation. Now this has got all 1411 readings in it. So as it drifted back down, or as the graph drifted down, the standard deviation would have fallen off. Like, this peak-to-peak value is awful for the precision of the DC calibrator, but it wasn't warmed up. I was showing the effects of warm-up. So what I'll do is I'll let this run some more, and I'll hop back in right before I shut the lab down for the night. I'm going to reset the buffer, so now we have no data, and we'll just watch. I'll give you guys what the standard deviation is after about another couple of hours of running, or about another hour of running. So we'll pick up readings for another hour, then I'll do a standard deviation, and that'll tell us just essentially a noise figure, how stable the reference is. The lower that number is, the more stable the reference. This is also comparing the noise of the meter at this point, because this meter's barely better in terms of stability than the calibrator is. So we're using two instruments we're measuring two instruments of the same class with each other. This DC reference needs some pretty fancy standards to calibrate it. That was one of the things I was worried about, because this is most definitely the best meter I have in the lab. But I'll let that run, and I will be back. Do my best not to disturb it as I'm moving around in the lab and everything like that, because even bringing my hands near the test leads would cause fluctuations and things like that. So we'll just let this run, and then we should be good. But other than that, I think this calibrator's in great shape. It's ready for a home on top of the 5200. So we've got a decent DC standard, and we've got a decent AC standard now in the lab. So can't calibrate this guy. I have to send him off to get calibrated, but he's the base. He's the highest precision piece of equipment I have in the lab at the moment. But we'll go from there. A little bit more than an hour later, but with 684 readings, so we have 684 samples, we have a standard deviation of 1.35 microvolts. We've also continued to trend down a little bit. We're now at 10.000008. So everything has continued to trend down, so incredibly stable, very little deviation. I can't ask for anything better. So it's in spec, everything's good to go. No reason why we can't do that, and I can just dial a voltage. I'll just pick a digit. Meters on it's high filtering, so it'll take a little bit to catch up. So we see a little bit of an offset. Obviously, it'll probably need some settling time, but I have 10, 9, 8, 7, 6, 5, 4 programmed into the calibrator, and it is just rock solid. Everything's good. Give it one more reading to update. Back down to 10 volts. So I cannot argue with that. Well, thanks for stopping by the lab, taking a look at this Fluke 3343A DC voltage calibrator. We'll be using this to maintain some of the meters and everything else in the lab so we can keep going with experiments. Also, it's a nicely adjustable DC supply as long as I don't want to supply anything less than 30 milliamp, but it'll go up to 1,000 volts, so everything is working well. I will see you guys in the comment section and the next video.